Hello and welcome everyone. In this class, you learn De Moivre's theorem and Euler's formula. De Moivre's theorem is used to solve complex number raised to powers and also to find the nth roots of a given complex number. Using Euler's theorem, you can express a complex number in its exponential form. Also, it is used to express trigonometric functions such as sin x, cos x, tan x as an infinite series in x. Now, De Moivre's theorem. The statement of this theorem goes like this. Cos of theta plus I sin theta whole power n is cos n theta plus I sin n theta. Remember, in order to apply this, real part of this expression, complex number, must be with cosine and the imaginary part must be in sine. So then you can multiply the argument, that is theta, by the power. So cos theta plus I sin theta whole power n is cos of n theta plus I sin of n theta, where n is any rational number. Sometimes cos theta plus I sin theta, briefly written as cis theta. So you can write the De Moivre's theorem as cis theta whole power n as cis of n theta. Now Euler's formula, it states that e power I theta equal to cos theta plus I sin theta. Using this Euler's formula, we can prove few important results. The first one is the product of cis alpha into cis beta can be written as cis of alpha plus beta. You can just add the arguments. When you have the product of two complex numbers in the cis theta form, that is cos alpha plus I sin alpha into cos beta plus I sin beta, that can be written as e power I alpha using this Euler's formula. The second term is e power I beta. When the bases are same, add the powers, you can get e power I times alpha plus beta. Again, using the Euler's formula, you get this as cos of alpha plus beta plus I times sin of alpha plus beta. The next one is reciprocal of cos theta plus I sin theta. 1 over cos theta plus I sin theta is 1 upon e power I theta. So this can be taken to the numerator, then the index becomes minus I theta. Again, using the Euler's formula, this can be written as cos of minus theta plus I sin of minus theta. Since cos of minus theta is cos theta itself and sin of minus theta is minus sin theta, you get 1 over cos theta plus I sin theta is nothing but the conjugate of cos theta plus I sin theta, which is cos theta minus I sin theta. Now, again using Euler's formula, you can prove this result, very simple result, but very, very useful. Cos alpha plus I sin alpha upon cos beta plus I sin beta can be written as e power I alpha upon e power I beta, that is e power I times alpha minus beta. So again using Euler's formula, this is cos of alpha minus beta plus I times sin of alpha minus beta. So this is a very important result. If theta is the argument of z, then the argument of conjugate of z is minus theta. Directly you can use in problems. If z is a complex number in its polar form, z is r times cos theta plus I sin theta, then its conjugate can be written as r times cos of minus theta plus I times sine of minus theta, because the argument of z bar will be minus theta. Now, two more important results. Square of z1 plus z2 is z1 square plus z2 square plus 2 times the real part of z1 into z2 bar. Here z1 and z2 are any two complex numbers. So here z1 minus z2 whole square becomes z1 square plus z2 square minus 2 times real part of the product z1 into z2 bar. Now consider this problem. Modulus of z1 plus z2 equal to modulus of z1 plus modulus of z2 is possible if one of these conditions are true. In other words, we need to find the condition for two complex numbers z1 and z2 satisfy the equation modulus of z1 plus z2 equal to mod z1 plus mod z2. So given modulus of z1 plus z2 is modulus of z1 plus modulus of z2. Now square on both the sides. You get mod z1 whole square plus modulus of z2 whole square plus 2 times the real part of z1 into z2 bar is equal to a plus b whole square formula here. Mod z1 square plus mod z2 square plus 2 times mod of z1 into mod of z2. On either side, these two get cancelled. So now 2 times real part of z1 z2 bar is same as 2 times modulus of z1 into modulus of z2. Let us call this as 1. Now we shall take z1 and z2 in polar form. Say that is r1 into cis of theta 1. Theta 1 is the argument of z1, which is same as modulus of z1 cis of theta 1. Similarly, z2 can be written as modulus of z2 into cis of theta 2. Theta 2 is the argument of z2. And therefore, conjugate of z2 will be modulus of z2 cis of minus theta 2. Now, if you take the product z1 into z2 bar, you get modulus of z1 into modulus of z2. Cis alpha into cis beta is cis of alpha plus beta. You can write it as cis of theta 1 minus theta 2. So further, you can write cis of theta 1 minus theta 2 as cos of theta 1 minus theta 2 plus I times sine of theta 1 minus theta 2. Substitute this in equation 1. You get 2 times. Now the real part is only this part, that is z1 z2 times cos of theta 1 minus theta 2. z1 into z2 cos of theta 1 minus theta 2, that is equal to 2 times mod z1 into mod z2. On either side, these two terms get cancelled, z1, z2 and 2. You'll be left with cos of theta 1 minus theta 2 is 1. So that gives us theta 1 minus theta 2 is 0. Theta 1 equal to theta 2. That is argument of z1 equal to argument of z2. So whenever argument of z1 equal to argument of z2, then the result modulus of z1 plus z2 equal to mod z1 plus mod z2 is true. Now consider this problem. Write the complex number z equal to 1 minus I upon cos of pi by 3 plus I sin of pi by 3 in the polar form. So first we shall write 1 minus I in the polar form. Z equal to 1 minus I. The modulus of Z is root of 1 square plus 1 square, that is root 2. Here 1 minus I lies in the fourth quadrant. Therefore, argument of Z, that is theta, is minus tan inverse of modulus of y by x, which is minus tan inverse of modulus of minus 1 upon 1, that is minus pi by 4. So you can write 1 minus I as root 2 times cos of minus pi by 4 plus I times sin of minus pi by 4. Now we shall substitute this in the given complex number. That is Z is 1 minus I root 2 times cos of, or you can simply write cis of minus pi by 4 upon cis of pi by 3. As we know, cis alpha upon cis beta is cis of alpha minus beta. This becomes root 2 times cis of minus pi by 4 minus pi by 3. That is root 2 times cos of minus 7 pi by 12 plus I into sin of minus 7 pi by 12. This is the required polar form. Now consider this problem. Write the complex number z. In the earlier problem, we had 1 minus I. Here, I minus 1 in the numerator. Denominator is same in the polar form. First, we shall express I minus 1 in the polar form. Say z is I minus 1. That is minus 1 plus I. Or the modulus of z is root of 1 plus 1 root 2. Z lies in the second quadrant. Therefore, its argument is pi minus tan inverse of modulus of y by x. That is pi minus tan inverse of 1 by minus 1 under modulus. That becomes pi minus tan inverse of 1, pi minus pi by 4, 3 pi by 4. So the polar form, we shall write it directly in the given set, is root 2 times cis of 3 pi by 4 upon cis of pi by 3. As before, you can write this as root 2 times cis of 3 pi by 4 minus pi by 3. That becomes root 2 times cis of 9 pi minus 4 pi upon 12. That is 5 pi by 12 root 2 times cos of 5 pi by 12 plus I sin of 5 pi by 12 is the required polar form.